Welcome to the Peacademia course on the basics of semiconductors. This lecture will cover the energy band. Let's start. By the time you finish this lesson, you will learn the atomic interaction versus the atomic distance, formation of the energy band, simple energy band, and the energy band a function of the interatomic distance. In the previous lecture, the idea of the energy diagram for an isolated atom was discussed. One example that I talked about was the silicon atom. You can see an isolated silicon atom and its energy diagram here. Of course, in the real world, we often are not dealing with isolated atoms, but materials consisting of millions or trillions of atoms. So what happens to the energy diagram when an atom interacts with adjacent atoms? To discuss this, let's imagine that there is another silicon atom in the vicinity, but is far enough so that the first silicon atom does not see or feel it. As a result, there is no interaction, and therefore we can observe no change in the energy diagram. If the second atom moves closer to the first atom, at a certain point, the last sublevels start to feel each other. According to Pauli's exclusion principle, no two electrons have the same 4 quantum numbers. To comply with Pauli's exclusion principle, the 3p sublevel of the silicon atoms splits into 2. Now, if the second atom moves closer, the 3s sublevel splits into 2. I'm pretty sure you can guess now what will happen if the second atom moves even closer. If this happens, the 2p sublevel splits by taking the second atom one more step closer, 2s splits. And by repeating this action one more time, 1s splits. The conclusion out of this discussion is that the process of energy splitting depends on the interatomic distance. A smaller interatomic distance results in splitting more inner energy sublevels. Now, consider a situation in which we have a big chunk of silicon material that has millions of atoms. What will happen to the energy diagram? The energy splitting takes place even in this situation, but since there are too many energy levels split and the energy levels are placed tightly beside each other, it is not possible to distinguish individual sublevels. What we can observe is a set of bands. This is why for materials we have the energy band, not the energy diagram. Those who watched the previous lectures in this course remember that the energy diagram did not have the x-axis. This is because we were focusing on an isolated atom. Now that we turned our focus to materials with n atoms, the x-axis becomes important and we need to take it into our consideration. The x-axis is the interatomic distance. I believe that concepts can be thought more easily through examples. As a result, I developed the discussion for the silicon atom, but it is conceptually applicable to other materials. Let's imagine that the temperature is 0 degrees Kelvin. The reason for this assumption is that at temperatures above 0 degrees Kelvin, the generation and recombination processes will take place, and I do not want to add too much of details in this discussion. Temperature also affects the interatomic distance. In the energy interatomic distance plane, as long as the interatomic distance is large enough, atoms do not feel each other. As a result, the energy sublevels are separate and no splitting takes place. The number of states available in the 1s sublevel is 2n. As a reminder, n is the number of atoms in the silicon material. A state refers to the maximum number of electrons a sublevel can host. 2s has 2n states, 2p 6n states, 3s 2n states, and 3p 6n states. All the states in all the sublevels are fully occupied except for 3p. In 3p, only 2 states are occupied by electrons and the rest is empty. By decreasing the interatomic distance, I get to a point where atoms in their last two sublevels 3p and 3s start to interact with each other. The sign of this interaction is that the energies in these two sublevels split and two bands are formed. By further decreasing the interatomic distance, the newborn energy bands merge. In the merged area, the total number of states is 8n. 4 states of 8n's are filled in this area. When the interatomic distance is further reduced, the band splits. This time, the number of states for both the upper and lower bands is 4n. All the states in the lower band are filled, however, all the states in the upper band are available. At some point, we get to the equilibrium interatomic distance. This distance for silicon is 2.35 angstrom. Angstrom is a unit of length and equals 10 to the power of minus 10 meter. At the equilibrium interatomic distance, the sublevels 2p, 2s, and 1s are yet to see each other, and therefore no splitting has happened to them. Further decreasing the interatomic distance beyond the equilibrium point requires the exertion of considerable pressure and energy. Although atoms do not go beyond the equilibrium interatomic distance under normal conditions, if for some reason that happened, the splitting could happen for the sublevels 2p, 2s, and 1s. By projecting the upper and lower limits of the top two bands on the y-axis at the equilibrium interatomic distance, we can draw two bands. The lower band is called valence and the upper band is called conduction. The gap between the valence and conduction band is called the forbidden gap. It is also called the energy gap. In the forbidden gap, there are no states available and therefore no electron exists in it. The energy gap depends on temperature. In silicon, increased temperature causes Eg to reduce. The reason is that increased temperature causes the material to expand. This means the interatomic distance increases. According to the energy interatomic distance diagram, when the interatomic distance decreases, the forbidden gap becomes smaller. In this lecture, I talked about the formation of the energy band and its difference from the energy diagram. I also introduced the energy band as a function of the interatomic distance. In the next lecture, I will cover the crystal structure. Thanks for joining this lecture of Peacademia.